CSIS 2430 is filmed before a live studio audience.
So let's start off with the basics here, okay? Propositional logic, what is it, what's its application, why does it matter to us, all this fun stuff. So take a look here. This is a list of a few things we're going to be talking about today. Just propositional logic, what the heck is that? Negation, compound propositions, using what we call conjunctions, disjunctions, conditionals, biconditionals. We're going to look at truth tables. Then we're going to look at notation, and then what are logical equivalences, and circuit reduction. All of the above we're going to try to get through today. If not, it's okay. We'll expand it till next week, but that's fine. So first off, what is the definition? What is its point? Why do we care about it? And the whole idea here is to construct mathematical arguments, or correct mathematical arguments, right? Correct ones. The idea is we take human English sentences and convert them into equations. Then we run these equations through a proof process, and we can prove that something is correct or incorrect, right? So here's some uses for that. Number one, you can use it to design circuits. This is something that was discovered long after propositional logic was even a thing, right? This comes from the, a couple thousand years ago, long time ago. But this circuit thing was recently discovered, maybe, I don't know, it's been about a good 80 years ago now, but it's been a while, okay? You can use it for creating programs, validating programs, right? So I'm going to show you some sentences here, and even though I haven't explicitly told you what is a proposition yet, I want to see if we can figure out if the following statements are propositions. And don't answer just yet, but I'm going to throw up a bunch of them up here. Number one, St. George is the capital of Utah. The question, and don't answer out loud yet, but the question is that a proposition or not? 7 minus 3 is 9. I have 12 puppies. Pigeons are reptiles. 4 plus 6 equals 10. And I can't even say that out loud. All right, so the question is, which of those are propositions? Let's look at the first one. Just shout out an answer. The first one, St. George is the capital of Utah. Is that a proposition? That is a proposition. How about 7 minus 3 equals 9? Is that a proposition? Yes, it is. I have 12 puppies. Yes. Now, I haven't told you what a proposition is yet, so if you're like, how do they know this? Don't panic. Pigeons are reptiles. Is that a proposition? Yeah. 4 plus 6 is 10. That last statement. They're all propositions. Yes, they're all propositions. Okay, so based on this definition, or based on this so far what we've looked at, what do we think a proposition is? Partially true, declarative statement, that's part of it. There's another component that must be there though. Something that can be proved to be true or false, or shown to be true or false. Right? Well, with that in mind, let's look at these statements again. What are the truth values of those statements? They're all propositions. What's the truth value of the first one? It is false. What's the truth value of the next one? Also false. Next one? Now, if it's unknown, can it be a proposition? Yeah, this one's fuzzy, right? Fuzzy puppies. This one's fuzzy because it's me, I can prove it one way or the other. The answer is no, I don't have 12 puppies. I would like to, but I don't. But there is some information missing there, right? So that one is a gray area. But if the fact that I can tell you or that I can show you or whatever, then we can say that that is truly a proposition and that its truth value is false. Pigeons are reptiles. False. It is a proposition, but its truth value is false. 4 plus 6, that is true. And you better all say the same answer on this one. No, it is false. False. The idea here is, what is a proposition? It's just what it sounds like. I am proposing the following. I propose that St. George is the capital of Utah. I am wrong, but that was my proposition. I propose that 7 minus 3 is 9. I'm wrong, but that's my proposition. I'm just proposing a statement that it's true or false. If it can be shown to be true or false, then it is a proposition. Simple enough. Okay. Next group. Again, hold your answers, but I'm asking the question, which of the following are propositions? We'll answer that in a moment. How many kids do you have? That's the first one. Eat an apple every day. X plus 5 equals 8. Y minus X equals Z. Let A equal 12. A plus 5 equals 19. So, is the first one a proposition? It is not. Why not? Yeah, it's not a declarative statement. It can't be proven true or false. It's a question. A question can never be a proposition. Okay? How about eat an apple every day? That's a declarative statement. It can't be proven. There's what is there to prove, right? If somebody said eating an apple every day is healthy or something, then it can be proven true or false, and then it can be a proposition. But that is not a proposition. Next up, X plus 5 equals 8. All right, here no's. Anybody want to vote for yes? No fights? Want to duke it out? State your case? See, it's in that fuzzy area, right? That's why, see, this one, based on the way it's written, officially is technically not a proposition. Just like the puppy thing, the way I wrote it, technically it wasn't really a proposition because I was leaving out a variable, how many puppies I had. There's some weird information missing there. But when there's a variable like this and you don't know the value of it, therefore you cannot prove it to be true or false, right? This one, they get a little fuzzy when you look at these, but these are technically not propositions, right? Therefore, the next one's not for the same reason, right? What about the last one? Yeah, it can be proven to be true or false, and we have enough information to do that. So this one is a proposition. What happened there? Check mark. There we go. So what are the truth values? Well, irrelevant. Irrelevant. What's the truth value of the last one? True. No? It's false. Yep. Look at that little weird tail on my F there. Why does it do that? Strange. That's both, yeah. All right, big picture. We feel okay about that idea? We kind of have a feel for what a proposition's all about? All right. Well, as I mentioned earlier, this stuff is old, right? This is Aristotle days, and it was originally called propositional calculus. So this has been around forever. If you've taken like a philosophy class, you've seen this stuff probably. If you've taken a discrete math class, which this is kind of that, it's a discrete structures, you've probably seen this before, okay? Sometimes even in calculus, this stuff comes up. Now here's the basic idea for the syntax. If I were to ask you in algebra, forget about this stuff we're talking about today, in algebra, and I'm going to represent a variable, or a number with a variable, what's the variable we always use? X, right? When you first, as a kid, learn about this whole thing with algebra, I remember when I was a kid, like next year we're gonna learn algebra, and they use letters instead of numbers. We were freaking out, right? They can say like 3 plus X. We just couldn't fathom how that could even work. In our world, we use P, Q, R, S, and so forth. Just like in algebra, you would start with X. If you need a second variable, what is it usually? And then Z and so forth, right? Sometimes you'll wrap around to A. Same idea here. We start with P, then go up the alphabet. True and false. We typically represent this with capital T or capital F. But because we want to look at this from the perspective of we're computer people, we're looking at binary, we're going to be looking at circuits, we are more interested in ones and zeros, even though I think most of my truth tables do have a true and a false in them. But we'll be looking at ones and zeros for sure in this context later in the semester. Okay? What about negation? What does that even mean? Yeah, so I can say, for example, this statement here, let P be the statement that St. George is the capital of Utah, right? Now I can just say P. I don't have to say St. George is the capital of Utah. I can just say P. Or in this case, P is not true, so it's not P, right? So you can use this negation symbols here, a little sort of a sideways L or 7 looking thing that goes next to the letter, or the line here that goes on top of the letter. And I'll show you examples of that in the next slide. Like that, okay? Both of those are the same thing. They're both pronounced not P. So the whole idea here is we take this long, lengthy proposition, we assign it the value P or Q or R or whatever, and then now I can simply say P, and that is the equivalent of, if X equals 5, I can just say X, and it's the same thing as saying 5, right? If P equals St. George's Capital of Utah, I can just say P, and it's the equivalent of that. But now I can do some math stuff with it because it's in variable form, right? And if I negate it, all I'm claiming is that whatever P is, it's not true, right? Now, there's multiple ways to do that. The reason you'll see the little weird symbol next to the P, typically what you'll see me use in, if I type something, is the tilde, because that key doesn't exist on a keyboard, right? And it's hard to put something above a letter. So I'll use a tilde, and that's relatively accepted in the math world to use a tilde symbol next to the thing to mean not. So you may see that. But this is how we pronounce it, not P. I had a student named Amanda who was actually in Sharknado number 4. She was in it like an extra in the background. I think she got eaten by one of the sharks or something like that. But so I did this just for her, for the class. And then her husband's also shows up in the thing somewhere. But the statement is Amanda was in Sharknado 4, The Fourth Awakens. Okay, that is a proposition, right? Next proposition I said was Nicolas Cage. Now her husband's initials were NC. So that's what that was all about, Nicolas Cage, NC. Nicolas Cage was in Matchstick Men. That's true, by the way. Also a good movie. If you haven't seen it, do so. Really good. Those are both propositions. Well, I can assign P equals Amanda was in Sharknado 4, The Fourth Awakens, and I can say R or Q or whatever equals Nicolas Cage was in Matchstick Men. Then I can say P, or I can say not P. I can say R or not R or Q or not Q or whatever. Okay. So what would the negation of those be? What would that sound like in English? Right? Amanda was not in Sharknado 4. And Nick Cage was not in Matchstick Men, right? So it looks like this. There's one way to do it. We just said that. There's another way to do it. And it is the preferred way for this class. Okay? This is valid. And if I see this, I'm not going to be upset. But this other way is preferred, and you'll see when I explain it why it's important. But it looks like this. It is not the case that Amanda was in Sharknado The Fourth Awakens. Or, it is not the case that Nick Cage was in Matchstick Men. Okay? Why do I want to do it that way? Any thoughts on why that is? Yeah, it's just easier to read, and it's especially when we start getting into making this stuff into formulas, it's much clearer if you do it this way. Because it's very easy to just take, whatever we assigned it to P and say, it is not the case that P is true. That's it. It's not this. Yeah. Yep. So you see what the original P was, and you can simply say, it is not the case that P is true. Okay, good. Any questions about any of that stuff right there? Just basic sort of foundational stuff here. It's pretty straightforward and pretty easy at first. Don't worry, I'll make it harder. I'll make it harder, but it gets harder. All right, so in the 1800s, this George Bull comes up with this book here. He writes this book, The Laws of Thought, and he takes this propositional calculus and he looks at it and realizes that this can be applied to Boolean. It's called Boolean logic, named after him, but sort of binary, which wasn't really a term back then, I don't think, but just true, false, yes, no kind of thing, where it can be applied in a lot of mathematical ways, right? And we're not going to get too heavily into it right now, but this leads us to a path that in the mid-1900s, along comes the circuit based on some of this stuff right here, okay? So where he discovered a lot of this stuff with the laws of thought. He discovered a lot of this stuff about compound propositions in the laws of thought. He wrote about it. And what do you suppose a compound proposition means? What do you think that means?
What's the meaning of this?
So you have proposition P, proposition Q, and now I have the combination of the two, P and Q, P or Q, something like that, right? Or there's way more complex versions of that, right? We'll see all of that. So it's just the creation of a new proposition based on old ones. All right, so let's take a look at some examples here. Let's P be the statement that Alex has 3 dogs, right? So Alex has 3 dogs. And let Q be the statement that Alex has 2 cats. Okay, so now I can just say P. And you know what that means. Alex has 3 dogs. Whether it's true or not is irrelevant. I used to have a friend that was a cop. I still have a friend who used to be a cop. I should say it that way. And you've heard, in the movies or whatever, they use all these numbers. So we got a 8-2 in progress or whatever. And I asked him, why do they do that? Like, you have to memorize all these numbers, that this code means domestic disturbance and this one means a traffic violation. Why do you memorize all that? And he said it makes communication more efficient. And I thought, why does it do that? Well, because 8-2, whatever that means, has a very specific meaning, that domestic violence or whatever, and I don't know if that's the real number, but it has a specific meaning. And so when you hear 8-2, there is no way to misinterpret that. It's a memorized meaning that we all know as police officers, right? And I think that's smart. Once you got to learn it first. That's the trick, right? This kind of reminds me of that a little bit, where I can just simply say this, and it's simple in an equation. Now, somewhere we have an answer key somewhere that tells us what this P stands for, but we're looking at the math of it, and that's the idea. Turn this stuff into math so we can manipulate it, right? All right. So I have 2 statements. Alex has 3 dogs, and I have another statement. Alex has 2 cats. We can use this symbol we call conjunction, which looks like the caret symbol above the 6 on your keyboard. It's not that, but it looks like that, right? And this is now called P and Q. How would we say that in English? Alex has 3 dogs and Alex has 2 cats, right? You have to be explicit as possible. Now we can use the disjunction and we get P what? Or Q. And you would say Alex has 3 dogs or Alex has 2 cats. Now, the way Aristotle says,
I have spoken.
He says when we use or, we mean it's implicit that there's both. This is not new to us in programming, right? What's that look like in programming? Yeah, if we have a statement like, I'll try to write it on the screen here. If x is equal to 9, whatever number that is, or y equals 7, awesome handwriting there, then do whatever's in the curly braces, right? Let's go, let's try to make that look like a 9, there we go. All right, sorry about the sloppiness there, but you get the idea. In this scenario, what happens if x is equal to 9? Does that code run? What if y is equal to 7? Does it run? What if they're both 9 and 7? Does it work? Yeah. So the implicit both in both cases, right? Now there is a thing called exclusive or, which we'll look at in a minute, which means only one of them can be true, not both, right? All right. We also know, by the way, just a little side note, I'm going to turn these into ampersands. That's a double ampersand there, which is and in the programming world, right? I know that's not a real ampersand. In that scenario, in order for P and Q to be true, P, for the want of a better term, and Q must be true, right? They both have to be true. Okay. All right. So we know this type of logic already. We're familiar with it. So Alex has 3 dogs, or Alex has 2 cats, or he has 3 dogs and 2 cats, and that fits we're fine, right? What does that tell you? If P and Q happens to be true, what is P or Q's status? Also true, right? Good. Now the exclusive or is this little symbol here is like a little target looking thing, right? A circle with a plus sign in it, okay? Some languages, they have this, and it's that you can actually just write XOR. That's the actual command to make an exclusive or. Different languages have that, right? This means this, though. Alex either has 3 dogs or Alex has 2 cats. It's implied that it's one or the other, but not both. This, by the way, is how humans speak in the real world. You go to Olive Garden and they say you can have soup or salad. Don't get both. You get one or the other. Most of the time when we say or in the human world, we mean exclusive or. That's just the way it happens, right? Make sense? All right, so again, this is, like I said, this is kind of the real world human speak. And so our brains are kind of wired that way. But we need to get used to whenever we use the word or, we really mean the other one, that's both can be true, right? We will hardly use exclusive or in this class. We might have a couple homework assignments, but we will hardly use that. All right, so in Boolean algebra, this is the stuff that George Boole talked about in his book, Laws of Thought. There are other ways to represent this stuff mathematically. So instead of saying P and Q, he might do something like this. P times Q, or also P times Q with a dot between them. Or what's another way to represent multiplying two things together with letters? Just put them next to each other, right? PQ, like that. Make sense? What about or? We will get into some Boolean algebra maybe towards the end of the semester, but I show you this now because some of your homework problems use this notation when I'm talking about a P and a Q or whatever, right? I just want to make sure you're used to the notation, okay? So let's take a look at a truth table. Why do we care about truth tables?
I want the truth!
Tell me what you said again, Daniel.
It's a quick, efficient way to see results.
Yeah, it's an easy way to see whether something is true or false or whatever, right? So let's first take a look at this. One combination, if I'm dealing with just two variables, P is Alex has 3 dogs, Q is Alex has 2 cats. There's one scenario where both of those things can be true. That's one combination of P and Q, right? Another combination is where one's true and the other's false. Third combination is one's false and the other's true. Fourth combination, they're both false. I asked Alex, they're both false. Okay. But these are the only 4 combinations. Do you agree with that? Is there any other way I can arrange true and false values with P and Q? Okay, you have to believe that before we move on. Okay, there are no other ways. You can believe that, or eventually it'll click, but that should be pretty clear. All right. Well, easy enough. Now, what is the value for not Q, or sorry, that's not P, for the first cell there underneath not P? What's the value? Not P. Yeah, it's the opposite of whatever P is. In the first situation here, P is true. Well, not that is false, right? So the first one we said is false. What's the next one? Also false, right? Because it's the opposite of this. So we said that's false, that's false. What's the next one? True. Next one? Yeah, it's the opposite of everything, right? False, false, true, true. Okay. How about not Q? First one is false. Next one? True. False. True, right? It's just these values will be the opposite of those values, right? Now, why do we use these? We've kind of discussed that a little bit, but we'll get to that in a minute. But do we understand the what? The actual application, the truth value of these? We understand why not P right here is false. Because I said that P was true. That's all. It's simply that. If I tell you P is true, well, then not P is false, right? Okay. What about P and Q? Remember, think about our coding logic, right? What has to be true for P and Q to be true? The whole thing to evaluate to true. They both have to be true. So what's the first value? True. Next value? False. 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 Right? Okay, we feel good about that? Again, think about this as parentheses, and that's an if statement. If P and Q, then run this code, right? Well, in order for that to be the case, both P and Q must be true, and in this case they are. Next case, the rest of the other 3 cases, they are not. There's at least one false in there, so that's false. Okay. Same thinking there. What do we have for this next group? True. Okay, next one. Also true. Next one. Also true, because again, one of them has to be true, and in this case, that one's true, and in the case above, that one was true. Last one? Last one is false, right? Because they're both false. Okay, exclusive OR. Let's try it. First one? False, because why? Right, in exclusive OR, it's one or the other can be true, and in this case, both of them are true, and that's no good. Okay, so that's false. Next one. True. Next one. True. Next one. False, because none of them are true. Okay, good. Feel okay about that? This can be a very useful tool, and we'll see it in action as we move along. Hey, any questions? Okay, here's where it starts to take a little turn. Okay? Conditional statements. Conditional statements are a little wonky. They're not hard, but they just take a little bit of stretching the brain to wrap your head around them. Here's the basic idea. Let P be the statement, I won the lottery. P, I won the lottery. Q is a statement, I will give you $1. Let P, therefore Q is how you say it, one of the ways you can say it. Let P, therefore Q be the compound statement, if I won the lottery, I will give you $1. Okay? That's how that is pronounced. That's how you say it. If I won the lottery, I will give you $1. P, therefore Q. Right? Now that's not too hard to wrap your head around. That's pretty straightforward. When it gets in the truth table, it's going to hurt a little bit. Now here's, there are a lot of ways to say this. Okay, and I'm going to show you a bunch of them. Some of them are like, oh yeah, that makes sense. Others, it's going to take you a minute to wrap your head around them, and we'll try to talk through each of them, okay? So here's a bunch of them. If P, then Q. I think that makes sense, right? If I win the lottery, you get $1. That makes sense. P implies Q. We okay with that one? And stop me if we're not. Don't feel like embarrassed because you're only one person that feels that way or whatever. Don't let that be a problem, okay? We'll look at it if we need to. Okay, if P, Q. Just P comma Q, right? If P, Q. If I win the lottery, I'll give you $1. So far, so good? Okay. P, only if Q. That one seems backwards, doesn't it? Right? So let's take a break and think about that one for just a minute. What this has to do with is we're talking about scenarios where that evaluates to true. Okay, that whole thing is a true statement. So I won the lottery and I gave you the $1. We're talking about only those scenarios, right? So P only if Q. Well, with that in mind, how does that make sense? P must be true only if Q is true. Think about that. Okay? And when we see it in the truth table, that'll make a little bit more sense, okay? In fact, let's hold off on the rest of these until we get the truth table answers up there, and that'll help clear it up a little bit, because there's a couple other ones, like this one's weird and this one's weird, okay? So let's look at those in details in just a minute. Let's look at it in a truth table though, right? P therefore Q. So I'm making the claim that if P, therefore Q, if I win, I will give you $1. So let me ask you, if I win the lottery and I don't give you $1, is this statement true? No, I lied, right? It's not true. If I win and give you $1, is it true? Yeah, because that's what I'm claiming. What if I give you $1 but I didn't win? That's where it gets tricky. Let's take a look at the first one. First one we agree is true, right? Because P is true, Q is true. Easy, right? Second one, we agree is false because P is Q, true is false. Agreed? Easy enough. Next one, though, I did not win, but I did give you $1.
Still think because you're not breaking.
That actually is true because I did not violate my claim. Okay, this is the stickiest part of this whole idea with the conditionals. But this one piece right here, and then the next thing we're going to look at here, must be understood to understand proofs. When we get into proofs, this has to be solid in your brain how this works. And we're gonna beat it to death today, so don't worry, we'll get there, okay? But think of it this way. I claimed I will give you $1 if I win the lottery. Well, let's say I give you the $1 right now. And in 10 years, I win the lottery. Well, it's true. You got your $1, I won the lottery. P therefore Q, right? If I win the lottery, I'll give you $1. Let's say I give you $1 right now and I never win the lottery. Well, you can't prove that I'm lying because I haven't won the lottery, right? Until I win the lottery, you cannot prove that that's a false statement. Only once I've won the lottery does any of it even matter, which is why the next one is what? True or false? You are correct. It's true. It is true. Yep, it's true because I never won the lottery. So therefore, you getting $1 is irrelevant, right? And the reason this matters is because when we're talking about proofs, the whole idea of a proof, like 99% of the time when you're dealing with a proof, this is the idea. based on your life of observation or experiments you've done or stuff you've kind of goofed around with, or just things that you sort of feel like you intuitively know, you come up with what's called a conjecture, which we're going to learn all about later. But you come up with what's called a conjecture. A conjecture is something that if you can prove it right, it's no longer a conjecture, it's called a theorem. You guys have heard of theorems. The Pythagorean theorem, right? Or Bayes' theorem, or these kinds of things, right? Why is it a theorem? Because it can be mathematically proven true. If you cannot mathematically prove it true, it's not a theorem, it's still conjecture. Once you've proven it true with some mathematical process, then now you advance to, I'm now a theorem, right? And I'm no longer a conjecture. And here's the proof that goes with the theorem to prove this is all true. Well, here's how proofs work. If P happens, I conjecture that Q will happen. Here's my theory, ready? Or my conjecture. If it rains, the ground will get wet, right? Well, if it doesn't rain, then it doesn't matter if the ground got wet or not, because I wasn't trying to prove anything about not rain. I was trying to prove something about when it does rain. So I'm not wrong yet. You haven't proven it wrong, right? So if I claim P, therefore Q, the only time I even process my proof or try to do anything is in the event that P occurred, right? And in fact, when we write proofs, which we will be doing, when you write the proof, the first thing you do is assume that P is true. Even if you don't know, even if it's not, you always assume it is, because the whole point of the proof is, well, unless P is true, none of this even matters. My whole point is because P happened, therefore Q will happen. Before we look at some of these definitions down here, how do we feel about the P, therefore Q? We okay with it? Okay? All right. Do we understand that one? As a way to Englishly say this, right, in human terms. Is Englishly a word? I don't know. We okay with that? This one. Okay. Look at the next one. P only if Q. This is one we started to talk about a second ago, but I decided to wait. P only if Q. Well, when I say P, what am I really saying? Forget that it's Alex has $3 or whatever. What am I saying when I talk about whatever letter? I'm saying P is true. That's what I'm saying. It is true that Alex has $3. That's what I'm claiming. Okay? So P is true only if Q is true. Now, P can be true where Q is false, right? So this seems like this is wrong. But remember, all of these statements are statements that you make when this whole thing is true. So what we're really saying is, in order for P, therefore Q to be true, then this is a valid way to say it. What that one's saying, the one that I have circled there, that circled bullet point, P only if Q, it's saying P is true. How about P must be true only if Q is true? That make sense? In order for this whole thing to evaluate to true, then P must be true only if Q is true. Dig it? Dig 'em. P is sufficient for Q. P being true is sufficient for Q to be true. Right? Pretty simple. And then the next one's the same thing, just a little more verbose. A sufficient condition for Q is P. Same idea, right? How about this one? Q if P. Yeah, if P Q, Q if P. Make sense? Pretty straightforward, okay? Q whenever P. Whenever P is true, then Q, right? Okay. Q when P, same thing. These two guys we'll come back to with your weird little tail there. I don't know what you're doing. We'll look at those two in a minute. Q follows from P, right? You got $1 follows from me winning the lottery, okay? This one. It's not quite a double negative. It's weird. So Q unless not P. Q must be true unless P is false. Then Q doesn't matter. That makes sense? That's all we're saying there. Okay, unless P is not true. Okay. Before I do those other two, we good on those? The rest of those? We good? Okay. Those other two, before I explain them, would you agree that they're the same thing? Like Q is necessary for P is a not as verbose way of saying a necessary condition for P is Q. Do you agree that they're just saying the same thing? What that thing is, we don't know yet, but would you agree that that's just another way to say that? If not, we'll look at it in baby steps here, okay? Q is necessary for P. What does that mean? Well, almost, yeah. So Q being true is necessary for P to be true, right? If P is true, Q must be true if we're claiming that whole thing's true. And all of these are making that claim, okay? A necessary condition for P is Q. For P to be true, Q must be true, right? Okay. What I would recommend you do, this is on page 6 in your book, okay? On your book in page 6, not right now, but after class or whatever, go make up 2 propositions, right? P, if I am tired, I will, P, I'm tired, Q, I will sleep. If P, therefore Q. And say them with these wordings here. Just try, just on scratch paper, try to figure it out. If P is, I'm tired. If P, then Q. If I'm tired, then I will sleep. P implies Q. I'm tired implies I will sleep. Just say them over until you can word them and they make sense in your head. And eventually, suddenly, bang! All right, we feel good about that? Okay, we're going to talk about this concept, this next concept in depth later. But when we get into proofs, there's this idea of a vacuous proof, right? So that something is vacuously true, and we've actually looked at it already. Okay, what we've been talking about, let me show you this here. This is actually a comic from C-Section Comics. It's a guy out on a date or something, and the girl apparently asked him, how smart am I? He's like, how smart am I? Let's just say that every research I ever published was featured in a distinguished scientific journal. Next date he's on, apparently the girl says, how good an athlete am I? Or she says, how good an athlete are you? He says, how good am I? Let's just say that I won all the marathons I've ever participated in. Okay, see where this is going, right? Ordinary people tell lies. Mathematicians tell vacuous truths. Okay? Here's the full comic, and you can see it at csectioncomics.com. Here's the truth. I publish a research paper. Q, my research, is featured in the distinguished journal. Right? P, therefore Q. If I never publish a paper, that statement is still true. It's vacuously true. That every paper I've ever written was featured in this journal. I just haven't written any. So it is vacuously true. It's true in a vacuum. You can't prove it wrong because I haven't written a paper. Next one. And this is true with me. Every marathon I've run, I won. Guess how many marathons I've run? 0, right? Make sense? So this is what's called vacuously true. In this situation where every one of these scenarios, he's full of it. He's lying. He's telling vacuous truths. They're all false. The left side, the P, is false in every scenario. Therefore, it's vacuously true. Until P occurs, it's not true. Does that make sense? All right, any questions about this so far? In proofs, this can be very useful. Eventually, there's going to come a time where we have used this truth table so many times here that we just intuitively know it. I mean, you know what not P is every time. It's the opposite of whatever P is. You know what not Q is. It's the opposite every time. Okay? This can be very handy in proofs later on down the road. We'll look at that. It's also useful in proving logical equivalences, which is extremely useful in proofs. Okay? So, for example, this is exactly the same as that. All right, now I'm going to prove that to you in a minute with the truth table, but I want you to look at that for a minute. P, therefore Q, not Q, therefore not P, are identical logically. First of all, what does that even mean, that they're logically identical? The idea is this. For any specific truth value combinations of P and Q, so let's pick true and false, whatever this evaluates to, this will also evaluate to exactly that. So what does that evaluate to right here in this scenario? False, right? P therefore Q. If the P is true and the Q is false, that evaluates to false. Well, if these are logically equivalent, then that will also evaluate to false in that scenario. That's what that means. All right, let's prove it though. I've censored this part. I've censored it for theatrical reasons. So let's take a look at this. I'm asking not Q, therefore not P. Well, what is in the first row not Q, therefore not P? We're saying true because not Q is that value, not P is that value. Well, when you have a false, therefore false, we've already established that's vacuously going to be true, right? Okay, so that's true. Next one. We hear false. Defend your position.
Not P is false.
So yeah, because not P is false, and that's the second half of the equation, right? Yep. First half is true, and if the first half is true, the second half must be true, or else you're going to get a false. Right? Okay, next one. True because the first half of the equation, right there, is false, and therefore the rest doesn't even matter, right? Last one. True because they're both true, right? Are you ready for the big reveal? And look what we have. Those two match each other. For the condition where P and Q are both true, both of those will evaluate to true. For the condition where P is true and Q is false, they will both evaluate to false, and so on down the line. Whenever every value is exactly the same in a truth table like that, they are said to be logically equivalent. Okay? This particular logical equivalence has a name, and it's called the contrapositive. The contrapositive can be very useful in solving a proof, right? So why would that be the case? If I said to you, that's a plus sign there, I don't know why my pen does that. So x plus 3 equals 7. Now, you guys know that x is 4, right? That's not hard. But when you first learn that, what was the trick to solving this that you have to figure out? You subtract 3 from both sides. Now, you weren't taught just, oh, subtract 3. You were taught this, that I can do anything I want to the left side of the equation as long as I do it to the right side of the equation. And when you first heard that in like whatever, 3rd grade, you're probably blown away, right? Like, really, you can do that? That's weird, that's crazy. So, if I wanted to solve for x, I could start by multiplying both sides by 17, then dividing both sides by 2.7. I can do that, it'd be stupid, but I can do that, right? Eventually though, the whole reason why did we choose 3, because the whole point of solving for x is try to isolate x. And so subtracting 3 is an easy way to isolate it, right? So it's an easy way to solve it. Well, this is the same kind of thing. This is a thing in your tool belt from algebra that you learned, hey, I can do the same thing on either side of the equation and it doesn't change anything. Well, here's the thing we just learned now is I can swap this for that in a proof and it doesn't change anything. But it might make it easier to solve, right? That's why we do this kind of stuff, okay? So we're going to look at a list of logical equivalences here, maybe today, but maybe next week. We're going to look at a list of logical equivalences. This is just one of many. And the truth table here helped us prove that the logical equivalence is correct. This is one of the main reasons we have the truth table, to prove the logical equivalence is correct. Once you've proven the logical equivalences are correct, then you just remember those or have the little chart of those, and you can use those. And you don't have to keep writing truth tables out, right? All right, so there's the contrapositive. P therefore Q, the contrapositive is you swap the variables and you negate both of them. P therefore Q is the same as not Q, therefore not P. Okay? Now the converse of this is Q therefore P. It is not logically equivalent. Okay, it is the converse of P therefore Q. It's not logically equivalent. But what would be the contrapositive of Q therefore P? Not P therefore not Q, right? You swap the variables and you negate them both. And that is exactly right. This, the contrapositive of it is that right there. Well, this thing is what we call the inverse of this thing. Okay? So if I dump them in the truth table, which you can prove that this is correct on your own, but if I dump them in the truth table, you'll see this is not the same as that. But these two cats are the same, right? The converse is the same as the inverse of the original right here. Again, it's a tool, it's a logical equivalence that can be useful in a proof, right? I don't expect you to memorize this, right? Everything's open book in this class, and in the real world, when you do this stuff, you still look stuff up. I mean, when you're writing code, how many times do you Google stuff, right? So again, note that the converse is logically equivalent. That's what the triple equals mean to the inverse. Any questions about that premise? Did I keep my promise that it's getting trickier? Okay, biconditional statements. So here we go. Let's go with P is a statement that you can drive my car. Q is a statement that you have a driver's license. This statement, written with a double arrow here, is pronounced P if and only if Q, if you're pronouncing it mathematically, is the compound statement you can drive my car if and only if you have a license. You have a license, then you can drive my car. If you can drive my car, then you must have a license. There's no way around it. No other rules. Now, in order for a biconditional to be true, each unique conditional must be true. P therefore Q must be true, Q therefore P must be true. They both have to be true in order for a biconditional to be true. So looking at this, how would we fill out this truth table? First one we're saying true, and why is that? Both of the conditionals are true, right? This statement here is true only if that and that are true. If the conditional and its converse are true. If both the original and the converse are true, then the biconditional is true. All right, that being the case now, what's the first answer? True, okay. How about the next one? Yeah, because one of them is false, right? This guy is false, even though that one's true, because remember, it's an and statement, right? Okay. Next one? False. Last one? True. Questions? So let's take a look at an example here where I want to know all of the possible truth values of this formula here. So I want to know if P is true and Q is true, what does this evaluate to? If P is true, Q is false, what's that evaluate to? If they're both false, what's it evaluate to, right? That's what I'm asking. I'm just asking you to make a truth table, right? So if I'm going to do that, then what stuff needs to be in our truth table? So those are the things we're going to need in the truth table. Why do we need them in the truth table? Well, I'm basically trying to figure out if this, we'll call this P for the want of a better term, therefore Q, right? I'm trying to figure out that whole thing's true. Well, in other words, I need to know if this side is true or false and if that side is true or false. Well, the only way to know that is if I know if that's true or false. The only way to know if that's true or false is if I know what P and Q is, right? So you have to keep drilling down. Same thing over here. The only way to know what that is right there is if I know each of those individually. Okay? So our truth table looks like that. The first three columns are easy, right? Just come up with all the possible combinations and then the negation. Okay? The next one, P or not Q. What is the answer to that first row? Q. Yeah, we're looking at P or this. Well, as long as one of them is true, we're good, right? Okay? Do we agree with that? All right, what about the next one? P and Q. First one's true. Rest of them are false, right? So now the final thing is we're saying this thing, therefore that thing. Well, that's this thing, therefore that thing, right? And so here we have a true-true. What's a true-true and a conditional? True. What about the next one? False. Next one? Next one's true, right? Because they're both false. And in a conditional, what's that?
Like vacuously?
Is vacuously true. Yep. Yep. And then the last one? False. Questions about any of that? Okay, order of operations, and then we're going to do a little activity that'll get you guys up and moving about. Okay? Now, technically, you could argue that this is first, second, third, fourth, and fifth order, because these are not interchangeable, and these are not interchangeable. Okay? So, but the first order of operation, just like in math where you multiply, divide, add, subtract, right? You do parentheses, the next one is first, right? PEMDAS. Same thing here. The first thing that gets evaluated is the negations. Next thing gets evaluated is the conjunctions, then disjunctions, then conditionals, and biconditionals. There are other things in between that we will learn another time, but for now, the ones we know, this is their order. My vote, however, always use parentheses. Then you don't have to think about it. To the whiteboards.